Okay, good evening, everybody. So let's begin our lecture. Uh, in the last lecture, we looked at the total number of multiplications and divisions in the Gaussian elimination process, and also calculated the number of, we did the operation count, and I think we also probably wrote the pseudocode and everything, right? So we did the pseudocode as well. So in the calculation of the number of multiplication and division, I made a small mistake. I hope you are able to find it. So we have a minus n plus n by 2.
It should be minus n by 3 if I'm not wrong. Yes.
Correct. Yeah. It should be minus n plus n by 2. It should be actually, instead of plus n by 2, it should be minus n by 3, right? So because, so you have minus n by 2 here. So this will become basically minus n by 2 instead of plus. And then this minus n by 2 together with the plus n by 6, it's going to basically give you, instead of plus 2n by 3, it's going to give you minus n by 3. It's going to be minus n upon 3. Okay, so that you may correct. Okay, and
but Professor Sir, that will not impact our order of what I'm going to say n cube.
It will not impact. Yes. It's not going to impact, but just that I wanted to make a correction here. That's all.
Okay.
Yeah, because the overall order is still order n cube by 3. Similarly, the total number of additions and subtractions will come out to be, if you have done it, it's going to come out to be n cube by 3 plus n square by 2 minus 5n by 6. Okay, so you may have obtained this one. Okay, so those are the corrections I wanted to make. Then let's get started with today's lecture. Okay, so today we're going to look at what is known as pivoting.
Professor, one thing I want to ask you. This,
Sure.
There is a funda called upper triangular matrix and lower triangular matrix, if I'm not wrong.
Correct.
So I could just check in one textbook that L into U is equal to some A, if I'm not wrong.
Correct, yeah.
And they have proven this concept. So if it is beyond the scope of this class, so can you just explain a bit of derivation on that?
No, we'll do that. That is the next in the syllabus.
Oh, okay, fine.
Yeah. So what we have done is the Gaussian elimination. What we will do next is the LU decomposition, which is basically nothing but a slight rearrangement of Gaussian elimination. If you are going to store these multipliers in a certain way, that is going to give you a lower triangular matrix. And then this matrix, whatever you have converted A into U, that will be your upper triangular matrix. So when you multiply this lower and triangular matrix and upper triangular matrix, this L times U is supposed to give you the A. Okay. So we'll come to that next. After we finish pivoting, we'll go to the LU decomposition. Okay.
Noted, sir. Thank you.
Yeah, sure. Any other questions, anybody, before we go to pivoting? So, okay, so pivoting basically is, there are two things. One is called partial pivoting, and then there is something called complete pivoting. Okay, so far, as somebody has asked in the previous lectures, we have assumed that this AKK supersede K, that means the pivot element that we are going to get, we assume that this pivot element is not equal to 0 anywhere in the process, right? That means whatever the diagonal element we're going to get, that is never 0. That is what we have assumed, right? Somebody asked, like, are we assuming this? Yes, we are assuming. But then sometimes this may not be 0, but it could be 0 except for the round off errors. That means it could be very small. So in those cases also, the answer is going to behave very, very differently, because the round off errors may kind of accumulate and grow as we are doing the calculation. So to demonstrate this, I'm going to start with an example. Okay, so we will consider this particular problem of two unknowns and two equations. The problem is given as 0.0003 x1 plus 1.566 x2 equals 1.569. Okay, and then the second equation is given as 0.3454 x1 plus 2.436 x2 is equal to 1.018. Okay, so basically we have two equations. We are asked to calculate what is the value of x1, x2. Okay. Now to solve this problem, we are also we are also given that use 4-digit floating point arithmetic with round off. Okay, so I'll explain you what is a 4-digit floating point arithmetic with round off. That means we can only store 4 digits as such. Okay, that means if we're going to get, let us say, some 1857.56, we're going to store it as just as 1857. Okay, or because it is with round off, we're going to store it as 1857.6, but then this will be rounded off to 1858. Okay, so that's how we are going to store. Similarly, if we're going to get, so that means we can only store 4 digits maximum, whether it is combined with all the decimals. That means if I'm going to get something like 0.00057, I'm going to store this as 0.0006. Okay, something like that. So this is basically, we are using round off and then truncating, or we are using round off, and then depending on if it is more than 0.5, we are adding 1 to the previous value and so on. Okay, this is how typically calculations in a computer work, and that is what we are asked to use. And then we have to calculate this particular solution from this problem, okay, from the given two equations. So we will proceed as before. We're going to write the augmented matrix, which is 0.0003, 1.566, and then 1.569. And we're going to write 0.3454, 2.436, and then 1.018. Okay, so that is my augmented matrix. So this is my A matrix, and right hand side is B. And we're going to start calculating what is, so my first row is my pivot row, right? And I'm going to calculate what is my M21. M21 is going to be 0.3454 upon 0.0003. Okay, that's what I'm going to calculate, which is going to give me 0.3454 divided by 0.0003. That's going to give me 1151.33. We're going to store this as 1151, right? Because we are only using 4-digit floating point arithmetic. Then we can write my row operation R2 equals R2 minus M21 times R1. That means the second row we are going to transform as R2 minus M21, that is this quantity, times R2, R1. Okay, so we're going to subtract off the first row multiplied with M21 from R2. Okay, that means the first row is going to remain the same, 0.0003, 1.566, 1.569. The second one, this is going to be 0. That's what I mean, at least our algorithm with the M21, it is supposed to be 0. And then this value is supposed to be essentially 1151 times 1.566. That is going to be 1802.466, right? But because it's 4-digit floating point arithmetic, this is going to become 1802.5. This is going to be 1803. Okay, this is going to be 1803, right? As what I have, and then I have 2.436 minus this minus, okay, sorry, this is minus 2.436. I basically noted is incorrect. This is a minus. This is a minus here, okay, in the given problem itself. So this is minus. So I have minus 2.436 minus 1803, right, is what I have, which is going to give me minus 2.436 minus 1803 is going to give me minus 1805, minus 1805.44. Okay, that means it's going to be minus 1804. So I'll write this as minus 1805 is what I'm getting. Okay, looks like there is some small mistake somewhere. I have 1151 and then 1.566. 1.566 multiplied by 1151 is going to be 1802.24. Okay, so this will be 0.25. Fine, this should be actually 180. Okay, so this will be 1805. Let us say keep this one. Okay, so then on the right hand side I have 1.569 times 1151 is going to be 1806. Okay, that will be 1806, and then with a minus, and then you have 1.018 minus 1806 is going to be minus 1805. Okay, this will be minus 1805. So that's going to give a value of x2 as minus 1805 divided by this one. That's going to give you a value of 1. And the value of x1 will come out to be, again, you can multiply this with 0.0003 x1 plus 1.566 times 1 equals 1.569. That's going to give you x2 equals 1.569 minus 1.566 divided by 0.0003. So I think I made a mistake somewhere. This should be 1804. Okay, I think we need to check that. Somewhere I made a mistake. This will come out to be minus 1804. Maybe I made a mistake somewhere here. Let me check. 1151 is what I have, and 1.566. Okay, that's correct. So will this be, this will be how much? Minus 180.2.466. Okay, so that will be minus 2.436 minus 1802.466. Yeah, this will come out to be minus 180.4.9, but this I am using with round off, which should actually become minus 1804. R1 0.0003. Okay. Okay, so this will become only 0.47. Okay, so this should be actually only 0.180. Okay, how much value will this be? If I'm going to use only 4-digit arithmetic with round off, this should be only
1802.
1802, right? This is only 1802. With 1802, this is going to be 1804 only. Okay, so this is going to be 1804. Minus 1804, that's going to basically give me 1804. So this will be, when I multiply this, we're going to get x2 equals 1805 divided by 1804. That's going to be 1.001. Okay, so that's what we're going to get. Multiplied with 1.001 equals 1.569. Then your x2 will come out to be about 3.33. Okay. So that means your solution is going to be, sorry, this is x1. Okay, so x1 is going to be 3.33. Then your solution is 3.333 and then 1.001. Okay, that's what you have, which is for x1, x2. If I had used the way directly it is. Okay. Now let me, but then if you substitute for these values in x1, x2, you'll see that it will not satisfy both the equations. Okay, so let me do a kind of a pivoting, or let me exchange the rows. Exchange the rows. That means instead of working with the first equation first, I'm going to work with the, I'm going to move the first equation to the top and then the second equation to the bottom. Okay, that means I'm going to work with the system where it is 0.3454. right, minus 2.436, 1.018. That is my second equation originally, which I'm writing first, and then this is going to be 0.0003, 1.566, and then I have 1.569. Okay, so this is basically, the first equation is written on the top, and then the second equation is written on the top, and then this first equation is here. Okay, so this was our original second equation, and this is our original first equation. I just interchange these two. Okay. And then what happens is that our pivot, which is M21, now is going to be 0.0003 divided by 0.3454. That is going to be 0.0009. Okay. So then if I do an R2 goes as R2 minus M2 R1, then what I would obtain basically is that the first row remains the same, 0.3454 minus 2.436, 1.018. Then what I have is, this is going to be 0. When I again calculate this, this is going to give you 1.568. This is going to give me 1.568. Okay. You can do those calculations. Then when you solve for x1, x2, you're basically going to get x1 equals 10, x2 equals 1. Okay. Now, the previous problem, when we have solved the first equation and second equation, we have obtained x1, x2 equals as 3.33 and then 1.001. Whereas when we have solved the second equation in the first place and first equation in the second place, my x1, x2 comes out to be 10 and 1. Now, which of these is correct? Now, this is happening, although, I mean, of course, if you substitute for 3.33 and 1.001 into the equations, you'll see that the 10.1 actually satisfies the original equations. But then this is not going to satisfy the original equation. Now, this is happening because of the round of errors that are happening. Okay. And together with the value of the pivot element. That means we have taken the pivot element as in the first example, we have taken the pivot element as 0.003, right? This was our pivot element, which is very small, right? So whenever we have values within an equation of varying orders of magnitude. For example, this one is of the order of 10 to the minus 4, right? 3 into 10 to the minus 4, whereas this is of the order of 1 and everything else is of the order of 1 or 0.1. So when we have elements of this order, then taking the pivot element as the small value as it is given in the problem is going to amplify your multiplier, right? When it amplifies your multiplier, then any small changes that we are making, like in terms of truncation or round off and so on, when it is involved with a finite precision calculations, like for example, in this case, we have used a 4-digit floating point arithmetic, but in reality, you may use maybe 8 digits or 6 digits and so on. So when we do that, then these round of errors will have a significant impact on the final solution that you would obtain. Okay. So as a result, it is always a good practice to keep the largest element as the pivot element, rather than whatever is the value that is given, which may not be the largest element. Okay. So what we have done here is that we have not changed the equations. Instead of writing the first equation first and the second equation later, we have interchanged them to just move the second equation to the top and then solve it. So as a result, our multiplier has become small instead of a very large value, and which is going to still preserve your answer, because the round of errors are going to be not affecting the solution so much. Okay. So the idea is to keep the largest possible element in the pivot position, right? That means, and for that we want to exchange the rows such that the largest value is in the particular row that we are considering. Okay, so this is basically is known as partial pivoting. That means if I were to do, let us say we have this matrix. So and then we have several elements, and we are doing calculation. Let us say this is the pivot element I have to operate on. Let us say I'm operating now on the second row. Then what I'll do is that I'm going to look for all the elements below this pivot element, right? And I'm going to check which is the largest value in this row. If the largest value is found somewhere else instead of here, then I'm going to move this entire row here, and then I'm going to move this entire row here. Okay, I'm going to shift this thing such that I'm going to get always the largest value in here. Okay, that's what my idea is. So we're going to get the largest value in here. Okay. So how do we do it? That means if I were to calculate, let us say Ck equal to maximum of a ik of K, where my I lies between K and N. That means if I am looking at, let us say, some kth row, and let us say kth column, and this is my I want my I to go from K plus 1 to K plus 1 to N, right? That means my I will start from K, or it will go from K plus 1 to N. That is what we're going to apply. But then I'm going to look for from the kth row onwards and then see. And when I do this, if my maximum element Ck, if maximum Ck is found for I greater than K, then switch ith row and kth row within the matrix. Okay. So that's what we're going to do. So that is basically known as partial pivoting. And that is what we have done in the previous problem, where we try to bring the largest possible element, which is 0.3454, to the pivot location. Okay. Now, there is also something that is known as complete pivoting, which is slightly complicated. Complete pivoting. That means what we will try to do is that in complete pivoting, not only we're going to look at the rows, not only we're going to look at the column values. For example, let us say if I am looking at some particular row, I'm going to look at all the elements in this row, in this column, as well as in all the rows that are there. Okay. If the largest element is found somewhere here, okay, or let us say if the largest element is found somewhere here, right, in some row, then I'm going to exchange this row for this row. Okay, then it will basically, the largest element will come somewhere here, and then I'm going to exchange this column for this column. Okay, but when we exchange the columns, we have to be careful, because exchanging rows is fine, because as long as you exchange your rows, your order of the unknowns remains the same. You have x1, x2 all the way to xn. Whereas when you exchange columns, you are changing the order of the unknown. So you have to keep track of column exchanges such that the unknowns are reversed at the or brought back to the original position after when the solution needs to be found. Okay, keep track of column exchanges so that they are replaced while calculating the solution vector. Okay, I hope this is clear. That means if I'm going to, because if we have, let us say, 2x1 plus 3x2 plus 5x3 equals 15.6, then if I'm going to exchange the columns, then I have to also exchange my unknown with it, right? For example, if I'm going to move this 3, like if I were to write this as 2, 3, 5, something like this, then I have x1, x2, x3 coming from a particular row. Then if I just exchange this 3 and 2, then my order of unknowns should be x2, x1, x3, right? Because if this goes here and this comes here. So we need to keep track of how many such things are happening, such that we also keep track of the unknowns, how they have kind of changed. Okay, so we need to keep track of that for the complete pivoting. So this is known as the complete pivoting. So in complete pivoting, we are going to scan the entire submatrix for the maximum value, and then that maximum value we're going to bring it to the pivot position. Whereas in partial pivoting, we are only going to scan all the rows below the pivot element, and we're going to bring the largest value to that position. Okay, so although complete pivoting is better than partial pivoting in terms of guarding against the round of error accumulation, generally partial pivoting is used in all the software, because partial pivoting is much more cheaper than complete pivoting. Okay, so partial pivoting is much cheaper than complete pivoting. As a result, partial pivoting is commonly used. Okay, Any questions so far? So if I were to write, that means if I were to write the complete pivoting algorithm or essentially value. So CK equals, we want to calculate the maximum value of Aij k, okay, where that means we want to look for all the values of rows and columns for that kth position, where this k would go from or the ij would go from k to n, right? Because we are looking at all the elements in the sub matrix that are there in the kth step, okay? And if I comes out to be greater than k, then exchange rows. And then if j comes out to be greater than k, then exchange columns. Okay, but then when exchanging columns, we have to be careful to put back the unknowns later. Okay, that needs to be done later. Fine. Questions so far?
Sir, one thing I want to ask you is that
Yeah.
basically in the complete pivoting, since we are exchanging the row and the column as well,
Correct.
and we are adding a complexity of keeping the gaze of what the variables will be, like if we're getting altered in that also.
Correct. Yes.
Instead
Yes.
of that, what is the fundamental, I would say, advantage we are getting compared to the partial pivoting?
The advantage is that, let's say, for example, if you have just like what we had in the previous problem, this element, this equation might have a very small value here. Let us say if this has a very small value or a very large value, you want to bring to the pivot position. Let us say you're doing 2, 3, 2, let us say, let's say there is a 5,000 and then 3 here. Then this large value is hidden, and which you want to bring to the front, as a pivot element. Otherwise, what will happen is that this can cause problems, or it is kind of both theoretically and numerically proved that this elements with large varying degrees of magnitude can cause the round of errors to grow within the operations quickly. And then we'll end up with a similar problem as we have ended up before, right? Instead of getting answer as 10.1, we'll basically get it as 3.3 and 1.001. So the idea is to keep the round of errors not grow while doing operations, and that can be obtained by keeping the largest possible element as the pivot element.
And sir, how much additional step it would introduce into the system because of this? And will that not be adding to the complexity of like computation in that way also?
How much more computational? Say it again, sorry.
Number of computation is going to be like added, and will that not be also be what I mean to say is complexity to the like software or like programming?
Definitely.
That you're going to have?
Definitely. See, for example, as I said before, we said we want to have AKK at K not equal to 0. Sometimes we say that AKK is, almost equal to 0. Let us say because of round of error or something, it is only non-zero because of the round of error. That means it could be, let us say, 1 into 10 power minus 5 minus 10 or something like that. So in which case we said you have to exchange with ith row with kth row. Okay, but then it is possible that everything below that element are also 0, right? In which case it is not possible to find a solution, and that indicates that your matrix A is actually singular because you are not able to find a non-zero element in that position. So that means the given matrix is singular. Of course, we are not going to work with those matrices for the purpose of the course, but then in real life you can get such matrices. Now your question is, there are two things. One is finding an accurate or correct answer. The other one is the computational complexity, right? Now, if we do not do, let us say, partial pivoting, or if we do not do pivoting in the first place, then we are not going to get correct answer, right? Because the answer you will get will not satisfy the original equation. That means you wanted to solve Ax equal to B, but then the A matrix has elements that are of varying orders of magnitude. As a result, without pivoting, the answer is incorrect. That means your X is not going to, you will obtain some X, but then if you multiply with that X again with A, you're not going to get B, which is of not use, right? Because you want to have a correct answer or at least an accurate answer so that you can go ahead with solving with the next step of the problem. But then now comes the computation complexity. So both partial pivoting and complete pivoting can be used to reduce the accumulation of round of errors as you are going. But then partial pivoting is somewhat cheaper compared to the complete pivoting. So that is where the trade-off comes into play. And then because you have to also not only move the ith row and jth row and then put these things back when you do it, generally partial pivoting is more preferred than complete pivoting.
Sir, one small question. When we make,
Yeah.
write the matrix, we know what's going to be the largest number and what's going to be the smallest number. So, as the Mij is going to be, we are going to follow the same process. At the beginning itself, we can do, right? Rather than doing it in between the steps, we can.
Oh, no. See, typically, okay. So typically, the matrices that you will work with are not going to be small, right?
Okay.
The matrices could be probably, let us say,
n cross n.
Yeah, it is essentially n cross n. But then this n can be as large as, for example, let us say if you're dealing with a finite element solver or a CFD solver and so on, this n is basically equal to number of degrees of freedom that you have, which could be of the order of few millions.
Yes.
Right? And then you will not have a nicely, obtained values in the matrix, because these matrices are typically filled from some parameters that you have, right? For example, my values within the matrix that I have here, I'm writing it as 2, 3.4 and so on. Usually they'll be typically filled from some coefficients, they may involve some delta x, delta y that we have in the problem, or some diffusion coefficients, or something else and so on. So usually these are all filled on the go, right? When you're solving for boundary conditions and we are solving for a particular time step and so on, these values are obtained from the neighboring cells that you have and from the cell that we are dealing with and so on, right? So as a result, you won't be able to, a priori look at all the values. See, for example, I have done, let us say, I have fixed my first row as pivot row, and then I have made all these as 0, right? When I do that, all these elements also have changed, correct? From whatever they are originally.
Agreed, sir.
Correct. So that means now I don't know. There could be an element which is very large, and there could be an element which is very small, right? Okay. Now this I cannot, only when I have done this row operations, I will be able to identify what is again the largest element and so on. Correct?
Okay.
Yeah. So we cannot.
Yeah, continue for this.
Yes. So essentially, that's what I wanted to say. Essentially, you have, let's say, A11, A12, all the way to A1n. We said we have A21, A22, and so on. So we have written it as Aij k, right? Where these things are changing with every step of that we are applying in the process. Correct?
Okay.
Yeah.
So one additional question.
Sure.
In the matrix, when we discussed, you told that it can be even 0, right? A2 to A3.
Correct. We end up with 0. Yes.
So, even in the initial condition, need not be after partial.
Sure. Yes. Possible. Correct. Yeah.
So, given this as a scenario, how do we?
Oh, okay. No, if the initial condition itself has a 0, that means the matrix is similar, right? That means the problem is not well posed. We have to go back and fix the problem in terms of, let us say, how it is defined, such that you are not going to get a singular matrix. Because if you have a singular matrix, then you don't have a solution that you can calculate, right? Otherwise, it may be possible that your solution is could be that you don't have a solution up to n values. Let's say you won't be able to find x1 to xn, but you will be able to find x1 to xn minus 1 only, right? Your xn value is basically some free value. You could choose anything, but then your system will still satisfy that. This is possible.
Okay.
Right? In which case we have to supply a matrix that is only of n minus 1 by n minus 1 size rather than n by n size.
Okay.
And then solve it. But that needs to come when you try to solve the problem, right?
Understood, sir.
Yeah. This is very much possible.
Thank you, sir.
Thank you. Other questions, anybody? In terms of partial pivoting and complete pivoting, the concept is clear, right?
Yes, sir.
Okay. How we are exchanging and stuff like that. Okay. Fine. So let me move on to a slightly different concept. This is known as the triangular factorization of a matrix. Okay. So what is triangular factorization of a matrix? So we have seen that when you are given A, when you apply Gaussian elimination, we are converting this into U, right? Matrix U. That means we are given Ax equal to B. We are performing row operations and converting it to Ux equals G. Okay, that's what we're doing. While doing so, we have defined several multipliers. For example, we have defined M21, M31 all the way to Mn1. And then we have defined what is M32, M33, and so on, M32, M42, and so on, Mn2, and so on, right? We have defined so many multipliers for each of the pivot rows. When we have fixed the first row as the pivot row, we have defined these many multipliers. When we fix the second row as the multiplier, we fix these many multipliers, and so on. Now, the idea is that in Gaussian elimination, or many times in physics simulations, let's say if you're doing some, again, a finite element model or a CFD method and so on, many a times, only the right-hand side keeps changing and your A matrix will remain the same for, let us say, for the entire time step within time step you are doing iterations or something like that. In which case, the calculating A to U is actually only one step. You don't want to do it multiple times, right? This we have seen in the context of calculating inverse also, right? When you're calculating what is inverse, we said Ax equal to I. That means I'm going to choose different right-hand side, E1, E2, E3, and so on. I'm going to get different X values, X1, X2, X3, and so on. And I'm going to use the same decomposition of A I have. So the idea is that now we will decompose A into a product of two matrices, which is a lower triangular matrix and an upper triangular matrix. And that is your triangular factorization. Okay, so that means here triangular means that one is a lower triangular, the other one is upper triangular. Okay. Now, how do we do this? So to do this, essentially, I'll go back to, I'm going to rearrange. I'm going to use the, we know that after performing row operations, we converted our A into U. But then we have also made use of several of these multipliers, right? I'm going to arrange these multipliers in a certain way so that that's going to give me a lower triangle looking matrix. Okay, that means I'm going to write all these multipliers that I have as, let us say I have 1, 0, 0, 0, 0 all the way to 0. And then I have M21, M31, and so on to Mn1. So these are the multipliers. So instead of throwing them after performing row operations, I'm going to keep them. Similarly, this is going to be 1, 0 all the way to 0. Then I have M32 all the way to Mn2. Then I have 1, 0 all the way to 0. And then this is going to be 1. Okay, so these are all my multipliers. And then one before that is going to be Mn minus 1, N minus 1, right? That is my multiplier before this. So this is what kind of a, how is this matrix looking like? This is looking like a lower triangle matrix, yeah, right? Because I have all ones along the diagonal, and then everything below that is all my m's that I have calculated before, and everything above the diagonal are all zeros. Okay, so this is a lower triangular matrix, and then I have the I have performed all these row operations, and then eventually obtained my upper triangular matrix, which was basically U11, U12 all the way to U1n, and then I have 0, U22 all the way to U2n, and then I have zeros here. And then I have 0, U33 all the way to U3n, and then I have UNN, and everything before this is also 0, right? So this is my U matrix. Of course, we realize that this is nothing but, I mean, I am using U's here, but this is nothing but my A's. So I have A111, A121. If I have to write in terms of A's, then this is basically A1 and 1. Then I have 0, A2, 2, 2, 2, A, 2, and 2, right? Because after the second step, this row is untouched. And then these are all zeros. And then I have A, N, N, N. Okay. So that is, this matrix is exactly same as this matrix. It's just that instead of A, I, J, K, that superscript, I'm using U, I, J, right? We said this is kind of easy. Now, I want to multiply these two matrices together. I have this lower triangular matrix. I have this upper triangular matrix. I want to multiply these two together and then see when I multiply these two matrices, L times U, am I getting my A matrix or not? Okay, that's what I want to do. So we look at a little bit of proof here that we're getting back or not, and then we will see how to decompose A into L and U. The idea is that instead of applying Gauss-Seidel and making all these multipliers and so on, we would like to decompose into two matrices, L and U, and then keep these L and U as the triangular factorization of the matrix A, such that we can solve for Ax equal to B for different right-hand sides using LU instead of A. How does that work? That's going to work like you want to solve for Ax equal to B. Okay. So instead of this, I'm going to decompose my A into a lower triangular matrix, a product of a lower triangular matrix and an upper triangular matrix, and I have LU times X equals B. And I want to call my U times X as some vector Y. Okay. Then this is going to be L times Y equals B. We know that L is a lower triangular matrix, right? That means this is basically a lower triangular matrix. This is all, that is all the values you have, and this is all zeros, times Y, which means Y1, Y2 all the way to Yn, equals B1, B2 all the way to Bn. I know what is the right hand side. I don't know what are Y's, but I know from the decomposition, I know from the A that is given, I somehow able to calculate what is L and U. Then I know what is this L matrix. I know all these coefficients. Then I can do, just like I have done backward substitution, I can do forward substitution here, right? Because I have only one element here, I have two elements here, I have three elements here. So first I can calculate what is Y1, then using Y1 and Y2, I can calculate Y2, and so on until Yn. That means I can do forward substitution and then calculate Y1 to Yn. So once I know Y1 to Yn, I know the Y matrix, then I'm going to plug it back here. And then now I already know U because I know A is decomposed into L and U. I know completely the values of L and U. Then here I have Ux equal to Y, where the right hand side is known, U is known. U is an upper triangular matrix. That means I know all these values times X, that means X1, X2 all the way to Xn, equals on the right hand side I have Y1, Y2 all the way to Yn, right? That means I can use backward substitution, calculate Xn first, calculate Xn minus 1, calculate Xn minus 2, and so on, right? All the way to Xn. That means I can now do back substitution and then calculate Xn to X1. Xn minus 1 all the way to X1, right? I can calculate this thing. So basically then what I have to do is that I just have to decompose A into LU once. Then every time my right hand side changes, I just have to do one forward substitution and then one backward substitution. That's all. That's all I have to do for every change in right hand side. I don't have to keep doing this A equals to LU every time. So this is basically exactly the same as the Gaussian elimination, but then this is a slightly different way in which we store and retrieve things such that we can do this for multiple right hand sides. Now the question is L times U, when we have arranged these multipliers, give us A back or not? So for that, let me look at this matrix. That means I'm going to look at this matrix which I have written. This is 1, right? The first element is 1, and then 0 all the way to 0. Then we have M2 1, 1, 0 all the way to 0, M3 1, M3 2, 1, 0 all the way to 0, and so on. Let us say I have Mi1, Mi2 all the way to 1 and then zeros, and then we have Mn1, Mn2 all the way to 1. Okay, that's my lower triangular matrix, and the upper triangular matrix is U11, U12 all the way to U1n, 0, U22, U2n. Similarly, we'll have zeros, U and n. Okay, that's what I have. Now let me look at multiplying one ith row with some jth column. Okay, that means I'm multiplying ith row with jth column. That means I should basically get, when I multiply these two, I have this matrix A. I have to get an element when I multiply this row with this column, right? I should get, I have one row and one column I'm multiplying. When you do multiplication of this and essentially sum all these elements, you're going to get one element in the A matrix, right? That's what I'm supposed to get. So let me write down what is ith row times jth column for a condition, let us say I less than or equal to j. Okay, let me take I less than or equal to j. And then write down this ith row. Ith row is going to be mi1, mi2, all the way. I'll have I minus 1. I is less than j, so we have I, right? I will be there, but I will be 1, right? Because we don't have MII, which is going to be MII minus 1, and then 1. After that is all zeros, right? That's the row that I'm basically going to obtain. And then my columns are going to be U1J, that is the column, U2J, all the way to, we are going to have UI minus 1J, then we're going to have UIJ, right? And then I is less than J, so it's going to continue, right? It's going to continue until UJJ, and then it will be zeros after that, right? That is my jth column, okay? Then when I multiply these two, I'm going to get Mi1 U1J plus Mi2 U2J and so on, plus Mi minus 1 Ui minus 1J plus this 1 times Uij plus 0 times Ui plus 1J and so on. So essentially these are all zeros, right? These will all be zeros after this. Okay, so I'm writing it as zeros after this. Okay, so that means we have these things. So that means what I have is I have this summation which is going from MIK UKJ, where my K is running from 1 to I minus 1 plus I have Uij, right? That's what I have, which is basically nothing but, I can write this as sigma K equals 1 to I minus 1 MIK UKJ is nothing but UKJ is nothing but AKJ at the kth step, right? Plus UIJ is nothing but AIJ at the ith step, right? According to our convention. If you're referring to a particular row, U value of that row is nothing but A value of that row at that ith step, after which it is not changed anymore, right? That's what I have. That means, again, if you go back to how we have updated, we have said Aij k plus 1 equals Aij k minus Mik Akj k, right? This is what we have used in the row operations in Gaussian elimination. That means I can write my Mik Akj as, from the above equation, Mik Akj k equals, it goes this side, so you have Aij k minus Aij k plus 1, right? I can write like this. That means I'm going to replace here sigma k equals 1 to I minus 1. Mik Akj, I'm going to replace it as Aij k minus Aij k plus 1, plus outside I have Aij I, okay? Okay, what does this mean? This means that k runs from 1 to I minus 1. So that means if I were to plug in 1 here, we're going to get Aij1 minus Aij1 plus 1, 2. That means this series, when expanded, is going to look like Aij1 minus Aij2. Okay, that is for the first term, k equals 1. Plus we have Aij2 minus Aij3 plus Aij3 minus Aij4 plus and so on, plus last element would be I minus 1. So that's going to be Aij I minus 1 minus Aiji, plus we have this outside Aiji. Okay. What is this value? This is nothing but the second term is going to be cancelled with the first term in the second, in the half term that is coming after. Similarly, this gets cancelled with this gets cancelled with this, and so on. And then this gets cancelled with this. Finally, this gets cancelled with this. And then we are left with only one term. That term is Aij1. What is Aij1? Aij1 is basically exactly the value of A, right, in the A matrix value of aij. 1 means it is the value available in the first step, right? That is the original value available in the matrix A, in A. That means when we multiply with this L times U for a particular ith row and jth column, we're going to get A for that. Of course, I have done this only for I less than or equal to j. Now, you can also do this, prove this for I greater than j. That means where your I is at a much bottom row than the column j. Okay, so as a result, you can do this for this particular second condition also. Okay, so which is yeah. So in which sense basically what we have proved is that arranging all the multipliers in a lower triangular matrix and working with the U matrix, we basically get back the matrix A. I'm not going to do this I greater than j condition. You can do it yourself. Otherwise, if we find time, we can probably do it in the next class. Okay. So that means now we have to find a way in which, of course, using Gaussian elimination, we can also calculate the LU decomposition of A, or else there is a direct method in which we can also calculate, which we're going to see next. Yeah, questions on this?
So contextually, if we take a 3x3 matrix, just to put a perspective to it,
sure.
What we used to do in a 3x3, I mean M21 will calculate, and then M31 will calculate, and then 32 will calculate.
Correct.
So we are technically trying to put a different, I mean, take out that M31 and M32 and create that as a matrix separately.
Correct.
And additional variable, the factor that comes out of it as a U vector.
Correct. So essentially, your A is getting converted into U. That remains as it is. But then when you are converting this A into U, you have several multipliers. All those multipliers, you are putting them wherever they belong. So as you said, this is essentially, let us say 100. 100, and then you have M21, M31, and this is 100. You have M32, M33 as such. Okay, or this is basically again 1, right? Because you don't have M33. Yeah. So that's all. So these three values, you put them as a lower triangular matrix.
Got it, sir.
Yes. So this is exactly what I will do later. Instead of M and U, I'm going to use some other variables, alpha and beta, to come up with a new algorithm where we can directly find M's instead of going through the Gaussian elimination process. Yeah.
Sir, technically, this is again a Gaussian elimination process.
This is exactly Gaussian elimination. It is exactly Gaussian elimination. It's just that in Gaussian elimination terms, you have converted Ax equal to B into Ux equals G. But then, if you don't store your multipliers, then you have this upper triangular matrix. But then, if I give you another B, instead of B, if I give you some B2, then you don't know how to get to G because you don't have those multipliers.
Okay.
Right? Because these multipliers are needed in converting the right hand side also. So as a result, what we're trying to do is that we are not worrying about B at all. We are factorizing A into LU, and then use LU with any right hand side by forward substitution and backward substitution.
So just if it is okay, can you elaborate on the second part?
Yeah. So what we did was, let us say if you have Ax equals B, right? You can use Gaussian elimination and then solve this as Ux equals G, and then apply back substitution and calculate what is X.
X, yeah.
Correct. Now, if I give you, you are done with this thing. Once you are done, you obtained U. You don't have any copy of multipliers or anything like that.
Okay.
Okay. I ask you to calculate again what is Ax equal to C. Okay.
Okay.
C is another right hand side. Now what will happen? Again, you will do row operations and make this Ux equals C, or Ux equals some right hand side. Instead of C, let us call it, instead of G, let us say Ux equals H.
Okay, but then
again you're doing the row operations, which are again order n cubed by 3, right? Which is not required, right? Which is not required. Rather, what you can do is that you don't have to work with different. You don't apply row operations. Rather, you you store your A, you decompose your A into LU, right? And then for any right hand side I gave you AX equal to B, you're going to solve A as LU, then you're done. Then you're going to only solve LUX equal to B, in which you say UX equals Y. So you solve for LY equals B and get Y. Once you get Y, you solve for UX equals Y and get X.
Clear, sir. Clear, sir.
Yeah. Then
So
any
you mean
right
to
hand
say,
side
sir,
I give.
like multipliers value are once calculated and stored, right? It's
Correct.
not going to
Exactly.
change.
Exactly. Correct. You store all the multipliers, and then that is going to, all the multipliers are going to form your lower triangular matrix.
So as long as L and U are not changing, even if you change the vector at right hand side, it will not be changing the solution. Or you
Yes.
can, without
Yes.
calculating whole matrix, you can just get it the value of X, Y, and Z, whatever.
Correct. As long as the A is not changing, most of the times it is so. You need to solve AX equal to B for different right hand sides. Now there is one question. I think there was some question that people have asked me before, where why are you defining M21 equals A21 by A11, right? We said Mij or A21 by A11, right? This is how I have defined. Somebody said, should I do it like this? But then should I do like, first row multiplied with some value, then second row multiplied with some value, and so on. So I think now it is clear why we are defining it like this, because when you define it like this, you will get back you get a lower triangular matrix, and then you can use it in the decomposition. But then if you use two factors like this, some value of R1 times some value of R2, then you cannot really get a single factor like that.
Sir, I would request one simple example, like what I'm going to say, where we can work on and understand this concept in a better way. Like theoretically, we have got it. It'll be very clear and solidify.
Yeah. So sure. Yeah, we will either I'll give it in the assignment, or maybe tomorrow what we'll do is that we will do LU decomposition slightly differently. We will not follow the process we have followed for Gaussian elimination, but we will say we want to calculate L and U directly from the product of L and U and a known A matrix. From that, it will be clear. Otherwise, I'll give you a small problem which you can solve. I think once we do that, we can solve the problem. That is easier.
Okay, sir.
Okay.
Fine.
So the complexity is going to be exactly same as Gaussian elimination, but the way you will calculate LU in LU decomposition is slightly different. We will not follow the Gaussian elimination process as such. We'll do slightly different. I'll explain that tomorrow.
Thank you, sir.
Okay, excellent. I think I'm going to stop here. I'll see you guys tomorrow at 4 o'clock. Unless you have any questions now. Yeah.
Thank you, sir.
Thank you, guys.
Thank you, sir.
Thank you. See you tomorrow at 4 o'clock.
Thank you, sir.
Thank you. Bye-bye.